My name is Julia Silge, and I'm a data scientist and software engineer at our studio. And I'm going to be working on some example projects to show how to address model ops tasks like model monitoring, model updating, model retraining. And in this screencast, I'm going to be walking through the first step, which is model training for the example data set that I'm going to be using for these example tasks. So this is going to look really similar to the screencasts I've been doing before, because it's how to take some data, do a little bit of model data exploration, and then how to train that model. But this data, it's not Tidy Tuesday data, it's some wild caught data. It's data from the City of Chicago's open data portal on traffic crashes. And we're going to build a model to predict for every traffic crash, did it cause injuries or not? And one of the things we'll notice about this data is that there's some changes over time as to maybe some seasonal effects as to how many crashes cause injuries. And so these are the kind of things that once we have a model, say that's in production somewhere, serving predictions, that as we monitor it over time, we may see changes. So this will be the first step in in the sort of steps in what we might call like a model life cycle, or the different kinds of things we might want to do with it. So let's get started.
All right, welcome. Let's get started. So let's look at this data from traffic crashes in Chicago. Like I said in the intro, this is going to be the first in a couple of videos about how to approach model ops tasks using using tools in R. So this first video is going to focus on training the model. And so this data set is great for demonstrating how to do model ops kind of tasks, because it's a data set that updates all the time. It's a data set of traffic crashes in Chicago. So, you know, there's unfortunately more traffic crashes happening all the time. So what we're going to do is we're going to build a model to predict whether a crash involved an injury or not. So we're going to get this data via an API that the City of Chicago makes available. So this data set comes from them. And so here's what we're going to do. The Socrata APIs, I think, are pretty nice. They're kind of nice to deal with. So we're going to make a little variable that says, we're going to take today minus 2 years. And so what this does is it says it takes the date that is today and then subtracts 2 years from it, so that we get when we do the query, we're going to get 2 years of data. I could have done 1, but I'm going to get 2 because that's going to be more data and better for the model. And then we're going to make a URL that has in it our query. So we can use Glue to do this. So the first thing we do is we put in the URL like this. So we put in the URL like this, and then we do a minus sign and then a $sign, and this is how we create the query. So we say where equals and then crash date greater than, and then we put in this years ago thing, which is what we made right here. So I just looked this up. Like, I looked this up in the R Socrata documentation, and I used the Glue, how Glue works, and I put it all together to make a URL here. And so what this URL is it will go back 2 years ago and look at look up and get for us all the traffic crashes over the last 2 years. So what we can do is we can call the main function from our Socrata, which is this read Socrata function, and we just pass it that URL. And so that what that does is it calls the API for us with our query, and so it goes to this data set with this query parameters and gives us back our data. So I'll wrap it in as tibble so that so this is a tibble, and then this will be our raw data. So it says, hey, I want all the traffic crashes in Chicago with the data that we have, and then I want, but I want it with this query parameter because I don't want all the traffic crashes from all time. I'll just want the last 2 years of data. So this will take a minute as it goes and does this call. So let's get ready here and say what we're gonna do next. I'm just gonna really quickly. I'm gonna do some things like with, okay, it's ready. So let's just quickly look at this. Let's do skim crash raw so we can look and see what it is that we have. All right, here we go. Let's make it a little bit bigger this way so you can see the little histograms. There we go. Okay, so we have about a little over 200,000 rows and 49 columns, which is quite a lot. We have things like the crash record ID, the traffic control device, the weather condition, the lighting condition, the crash type, report type. We have, so these are all the characters, the character variables. How many are empty? How many are unique? So you can tell, so things like IDs are unique, of course. And then there's many lower. We have these numerics, the speed limit, injuries, whether there are injuries or not. And so there's all these different ways of measuring the injuries. How are they fatal or the total? Is it unknown? The crash hour, the crash day of the week. We can find that, of course, from the crash date if we wanted to. And here are the little histograms. And we have the crash date. When were the police notified? Because sometimes that's not the same date, and not. So there's a ton of information here. I'm gonna walk through a little bit of exploratory data analysis, and then we are going to build a model to predict this. So this is a model that I have actually looked at this data a bit ahead of time. So I'm going to walk through what I think a good model is for this data, given the constraints of what we're going to try to do next over the next couple of videos with this. One thing I want to look at here, crash raw. So the report type is we have on scene. So was the report about the injury made on scene? Was it not on the scene, like a desk report? And then there's these empty ones. I think I'm just going to fill that in. All right, so there's 40 variables, a lot. I think I'm going to cut this down a little bit. And then there are quite a lot of them that have these missing as well. So I think for this analysis, we are going to filter to, we're going to choose variables that we have that we're going to use, and then we are going to filter out NA things that are complete, that we have everything. So let's do a transmute here. And so let's use this injuries total that we have here. It is mostly complete. And what we're going to do is we're going to say if, let's say injuries, if else. So if injuries total is greater than 0, let's say let's call that injuries, and if else, let's call it none. So this is going to be our outcome, the thing that we're going to try to predict. We're going to try to predict whether a crash involved an injury or not from the other things that happen. So this, we're going to, ask questions like, is a traffic crash more likely to cause an injury at night versus during the day, or on the weekend versus during the weekday, or in certain locations and whatnot. So that's the kind of model that we're going to try to that we are going to try to build here. So let's keep things like crash date, crash hour. Let's keep that report type that I just showed, and let's do another if else thing here. And it's if report type, if it was that empty thing there, let's call it unknown. And otherwise, let's just keep what it was, like that. Let's see. So there was something called, it was numeric, I think. Number of units. So this is how many cars were involved, or vehicles. Because sometimes some of these are like pedestrians, some of these are bicycles. So let's keep that num units. Let's keep that posted speed limit, weather condition, lighting condition, roadway surface condition, first crash type, traffic way type, primary contributing cause, and then let's keep latitude and longitude so we can see if there's something to do with where these are. That is important. And then let's only keep because we don't want to, especially things that we are missing, like injuries, we don't want to keep those. We won't be able to train a model for that. Okay. So let's see what we have here. How many do we have? Okay, that only got rid of a few. So this is good. This is good. Let's keep this. Okay, so now let's do a little bit of some exploratory data analysis here. So first, I am interested in how this is changing over time. So let's take that date and let's use this floor date function. And let's so what we're doing here is we're like rounding down to the nearest week, and then we're gonna count crash date injuries like this. And so we're saying in every week how many injuries versus not injuries are there. And then we're going to say, we're going to put the crash date on the x-axis, n on the y-axis, and let's color by injuries like this. And then a plus, and let's put lines and make them a little bit transparent. And let's see what that looks like. All right. So first of all, I think I must not have run this theme light, which means I must not have run all of that, maybe. Okay. So a lot going on in this plot. Okay. So first of all, 2020. Wow, everybody. Look at that. That's 2020, right? That's the lockdowns from 2020 right there. That's incredible. Truly, truly incredible. Okay, let's, so what's going on with these edge effects? Those are weeks that don't have, they're not full weeks. So what we want to do is after we count, we want to filter out so that the crash date is not equal to the last crash date, and the crash date is not equal to the first crash date. This is so nice whenever you're doing things like this where you count it up like weeks or something to take it out. Okay, there we go. Much better. And we want to make sure we have 0 in this plot. So so scale y continuous. So I say limits equals c, 0, and a, like that. Okay. There we go. Okay, so this is count. This is injuries per week over time, over the last 2 years. So fortunately, injuries are more rare than non-injuries, but this does tell us we have an imbalanced class problem. So we'll need to keep that in mind as we build our model. Boy, I mean, look at that. That is incredible, right? Like, that's the effect of 2020. This is, I mean, I've heard people talking about this, but this is like every time series that we deal with for the rest of our careers, right? Is like, there's 2020. Okay, so I copied this and I just want to, instead of looking at the counts, because what we're actually going to be modeling is for any given injury, for every given trash, what is the likelihood that it has that an injury took place. And so we want to look at what is the proportions of injuries over time. So group by crash date. Let's say mutate percent injury and divided by some n. And then, whoops, that's too many things. And then let's do ungroup. And let's filter. So if we do that, I'm just going to show you what it looks like here. So we've got injuries, no injuries, injuries, no injuries. So we want to filter just to injuries equals injuries, like that. And take out that. And what do we want to do? Maybe we just want to make it a color instead of a black line. I think the rest of it should be the same. Oh, except now it's a percent. So we'll say labels equals percent format, like that. All right. Okay. So, does that line up? It doesn't. Let's see. It does line up. Okay. So this is, oh gosh, limits. Labels, I need to change, this is wrong now. Scale, limits, labels, percent, format, because this is obviously not right anymore. So limits equals labels, y, instead of n, we put percent. Oh, well, that's why it's the same. Because I was literally plotting the same thing. Okay, right. Okay, so this looks better. So this is now the percent of injuries that, the percent of crashes that have an injury over time. So there is some change over time, but we now don't see like some huge change due to the lockdown. Instead, we see maybe like some seasonal pattern, maybe like over the winter into summer, maybe like over the 2 years, possibly, and maybe like an increase over time, possibly. So this is what we're modeling, is this proportion. And notice that there is change over time. And so this is often what happen in real life when you're building a model. You build a model with some data, and then you run into what's called model drift. So as you build a model, you use good practices when it comes to data splitting, splitting into training and testing, and then the underlying distribution of what you're modeling, it changes. And so as you predict against your model over time, you have what people call this concept drift or model drift, or people use different words to talk about it. But so you have to do what's called model monitoring to understand at what point is your model not a good reflection anymore of the reality of what it is that you're looking at. So this data set, I think, is a great opportunity for us to kind of see what's going to go on together in the real world, because it really does have model drift. It's going to have model drift over time. And we can see this model, put it into production, watch it have predictions, and then see what it is that it does. So before we go and do the model, let's just look at a couple more exploratory plots. So let's look at, for example, the weekdays. Crash date, weekday of crash date. This is a function from Lubridate. So if we say label equals true, this will count up. So let's count it up. So count crash date injuries like this. So we can say how many injuries versus not injuries were there on the different dates. And then we can say group by injuries, and let's say mutate percent equals n divided by sum n, and we can ungroup. And then here's what we're going to do. We're going to put percent on the x-axis, crash date on the y-axis, and then fill equals injuries, and geom call with position equals dodge, so that they're like right next to each other. Each little bar is going to be right next to each other. And then let's do a scale x continuous and say labels equals, let's do library scale so I don't have to keep doing it every time. Percent format like this. So let's do this. So what we have here is the percent of crashes on each day and whether there was injuries or not. So it looks like on Friday, there's proportionally, there's fewer injury accidents, maybe because there's just more, accidents overall. So more just like non-injury accidents. But Sunday, there's fewer accidents, but more of them are injuries and whatnot. So we can do this if I copy this and paste it, and I'm going to say, let me take this out, and let's do count first crash type. And then I think I'm going to make that first crash type. I'm going to fact reorder first crash type by n. So they're in a nice order. And then I'm going to do this same thing. And then I'm gonna have to filter, because that's gonna be a lot of them. There's a lot. So let's filter, let's group by first crash type. And let's only keep ones that there's at least 1,000 for. 10,000, sorry. Okay, and so crash date becomes first crash type. The rest of it stays the same. So this is going to be the same kind of plot, but shows us by first crash type. So if the first crash type was with a parked motor vehicle, then you're not likely to have injuries. But if your first crash type was at an angle, then you're much more likely to have injuries. So that's what we can make this kind of we can make this kind of plot. We could do this for like lighting condition and weather and all this kind of thing. But in the interest of like getting to the model, let's move on. Let's make one more plot because I love maps. Everybody loves maps. Let's do longitude, latitude. Let's say color equals injuries. And let's say geom point size equals. Let's make them little. They're going to have to be very transparent, I bet. And that's all, I think. Those colors, I bet, are going to be hard to see, but I don't know. Let's see what it looks like. It's a lot of points. So right now it's plotting, you know, several 100,000 points. Ah, okay. So some of them are at 0, 0. So that means they didn't know latitude and longitude, so they just put in 0, 0. I bet it's not that many, but we may want to, well, certainly for the latitude greater than, we want to filter them out. Those colors are going to look bad on a map. Scale, color, let's see if we can get this right. Scale, color, manual, and then we say values, and then we put 2 colors, like, I don't know, deep pink for, and then like a really light gray, like really light. Okay. Okay, so we might want to, I don't know, like, we should see how many of those there are. Ah, that's Chicago. Look, it's Chicago. Let's wait for it to render. You can do it, computer. There, that's Chicago. There we go. Okay, and so the pink ones are the ones with injuries, and the light gray ones are the ones without. And so I don't know. I would maybe believe that there's patterns in there. We'll see if our model can learn that there are patterns there or not. And you know, I don't know. We could maybe either leave the zeros and see if that is informative, that having a 0 in latitude and longitude is 0, or we can count that up or whatever. Let's you know, let's leave it there for now. So, okay, so now that is exploratory data analysis. And now let's move on to building our model. So let's set a seed. And let's first do our initial split, where we're going to split into testing and training. So this will be crash split. And we will split, so the training of crash split. So we'll call this crash train. And then crash test will be testing of the split. So that's training and testing. And then let's make some resampling folds. Let's use a let's use tenfold cross validation. So we resample the training set, and we can do that with stratification as well, so that we have the same. And that's probably a good idea here, because remember, the injuries, that's a minority class. We have class imbalance, so it's probably a good idea to use stratification in this situation. So we can have our resampling folds. So let's look at this. Okay, so our training data, we have this is how much data we have for testing and training. Sorry, for training and testing, yes. And then our folds look like this. So within each resampling fold, we have this much data for analysis, like training, and this much data for assessment, which is like testing. And okay, so now let's create our model. So the model, I did actually look at this a little bit ahead of time, and so I tried a couple different kinds of model, like a random forest and an XGBoost model. And what I ended up landing on is, I'll do the model here. You know what? I'm just gonna do it all in one thing. So the model that I'm making here is a bagged tree model. So we use we load the baguette package to do it. So we use, whoops, baguette. So it's a bagged tree model. And so what is nice about it, I'm going to say min n of 10. So that's the, so if I do bag tree, that's the minimum number of data points to split. So min n, it's smaller as a default, and we actually have a lot of, data here, so we want to make it go up a little bit. So I'm going to set the engine to be R part, and I'm going to bag, how many times am I going to do bagging? 25. So that's, kind of medium, I guess. And I'm going to set the mode to be classification. So why am I using a bagged tree model? When I looked at the couple of kind of models I tried, including like random forests and XGBoost, the bagged tree model worked just about it, like almost exactly as well. But it is much, much smaller in terms of the model size, like the object of what we will need to predict from. And it's way faster to train. So basically we get as good performance for much faster prediction and much faster training and much smaller footprint in what we'll need to save for deploying the model. So and those are real world things we need to worry about when it comes to model ops kinds of things. So that's where we're going to make our bagged tree model. And a tree model, I think, is a good idea here because this kind of like there's a lot of complex interactions that are important in whether an injury crash has an injury in it, like all these things about weather condition and lighting and first crash type and contributing cause and all this kind of thing. And so tree models are good at learning those. And so, but there's a lot of different ways you can implement tree models, like XGBoost and random forest. And bagged trees are it turns out in this situation, we got a really good performance or as good performance as these other ways, but at a much lighter weight footprint. So that's the model that we're going to use. We're going to do pre-processing using a recipe. So we're predicting injuries based on everything else we have. We give it the training data so that it knows what data we're dealing with. And then we're going to do a couple of things. So we're going to take that date that we have and we're going to create some date. We're going to create basically all the date features that we can have. So what date does is it creates date data. So what date of the week, month, and year features from the date that we have. And then after that, we can remove the date column. So instead of trying to predict the actual date, which is not really a good idea and what we want, we're going to have these features: day of the week, like Saturday, Monday, Tuesday, month, and year. And so since we're doing a tree model, it's going to be able to learn rules like, was it March of 2020? Did something weird happen in March and April of 2020? So it's, we're giving the model the opportunity to learn that. We're going to do step other for, remember when I said, hey, I have to filter for first crash type because it has so many levels. So that is true of a lot of these things. So we're going to do step other on weather condition, first crash type, traffic way type, primary contributory cause. Let's hope I did that right. And we're gonna all those things are in all caps, so let's keep that. So these, okay, so let's do that. These things actually all are in all caps, and some of them have some of them have spaces and other things that are maybe not as clean as I would like in terms of how we're going to predict, how we're going to have this at the end. So another thing we can do here, I wonder if that's important. I was going to step clean levels it, but maybe that's not so important. Maybe we'll try skipping that and see how it goes. One thing that is important is we are going to do step down sample, and we are going to down sample the injuries at the injuries level. And that is from the Themis package. So we have imbalanced data, remember. And so down sampling, that may seem crazy, like I'm just going to throw away so much of my data, but it actually does help your model in many situations, that the model performs better on testing data on new data when you throw away a lot of your data, when you throw away in a principled fashion. Okay, so this is going to be our pre-processing data. Some of the most just like the important things here are we're creating date features. We are handling the really high factor levels that we have. We are handling our class imbalance. We're using a bagged tree model because of its nice characteristics for this data that has so many complicated interactions. Now let's put this together in a workflow. So we start with a workflow. We are going to add the recipe here, and we're going to add the model, which is the tree model, and now we will have this all together. All right, so this is ready. It is ready to go. So let's register my parallel backend, and I'm going to use fit resamples here to this. So I give it my workflow. I have my folds, and I am going to save the predictions so that I can do, why do I want to save the predictions? Actually, maybe I don't need to save the predictions. Yeah, actually, I don't need to save the predictions. I'm not going to do that. I'm not going to save the predictions in, we're going to try to do this as lean and streamlined as possible. So it is now, whoops, what did I do wrong? Weather condition. Let's try that again. Condition. All right. Here's my big tip for today is that it helps to it really helps to spell your variable names right, takeaway for today. So what it's doing now is for each of the 10 cross-validation folds, it is fitting this model to the analysis part of the fold, and then evaluating on the assessment part of the fold. And what this is going to do is it's going to allow us to understand on our training data how does this model perform. And it was this kind of analysis that I did on, a random forest and XGBoost and a couple different kind of things, looking at the training data that, and including like tuning XGBoost and whatnot, that I was like, you know what, this bag tree model does great and trains quite quickly, trains much, much faster than the other options that we have available to us. So we're gonna do that, and then let's talk about how we're gonna evaluate the model. So we're going to be able to, once we have this model here, we're going to be able to look at the metrics of the model. We'll be able to look at the metrics. We just use the default metrics that we have for a model like this one, which are accuracy and area under the curve for the ROC curve, and Let's see. I wonder how much longer it's going to take. When we use a parallel backend, we unfortunately don't get logging because the logging is within the processes over in the parallel process. Okay, there it's finished. So here we go. So here are the metrics. So these metrics and accuracy and the metrics of accuracy and area under the curve here are almost exactly what we achieved when we looked at things like random forest and XGBoost. And so this is about as good as we can do with this data. So this is about as good as we can, we have these variables for any given traffic crash. This is about as good as we can do to predict whether there is an injury or not. Not too bad, if you ask me. So let's now fit one more time. So I'm going to use the function last fit, which fits one more time to the whole training set, and then evaluates on the whole testing set, which we have not touched yet. We have not looked at yet in this analysis. So we're fitting one more time, but now in a much faster way. This will be much faster because it's just fitting one time on the training set, and then we'll evaluate on the testing set. And so once that is done, we'll be able to collect metrics on this object that has been fit. And these metrics here that we have here are on our resampled metrics from the training set. And then the metrics that we'll get out here are metrics on the testing set. And we're going to save this information that we have. And then after we deploy this model, we'll be able to make predictions on new data. And then when we can compare that to these values, we'll be able to say, hey, how's it doing? Are we getting about what we expect? So here now are the predictions on the testing set. So this is about, what we expect. 1, 2, 3. This is about what we expect on the testing set, given how we did on the training set. So no huge surprise here. So we can now do a few more things. For example, we can take crash fit, and we can look at that workflow. We actually have to get it out like this, which isn't super beautiful, but it has within it variable importance scores. We actually get that out automatically from bagged classification trees, which is really nice. And look at the things that are most important. Report type. Remember that was the two big ones was the report taken at the scene, or was the report done later? Like was it called in later to someone at the desk? So that can make sense, right? Like that if there was an injury and the report was done at the scene because the police had to come out. Latitude and longitude is also important. That may be related also to the report type. So this isn't like causal, but in fact it's the other way, right? But it helps us understand which way it goes. First crash type also really important. Remember, we looked at that, and that is this one is now we are getting to something causal, like whether the crash was with a parked car and whatnot. We can make a nice we can save this, pull workflow fit. We can pull out the fit, and let's call this crash importance imp like this. And we can get out the crash fit importance, and we can say, let's take the top, so value, let's take the top 10 like this, and we can make a little plot. We'll put value on the x-axis term value on the y-axis, and then a bar chart. 8. Like so. Whoops, what'd I do wrong? Midnight blue. There we go. All right, and so this shows us visually how important these different terms are for this bag tree model. So we have the report type, latitude and longitude, first crash type, month, crash hour, day of the week. So these date features are quite important. Traffic way type, and so forth. So these are the most important things for weather, the most important contributing factors to very important variables globally for the model as a whole, for what it causes a for predictions of injuries. We can do an ROC curve for the test set. Let's see. So this is crash fit group by, no, let's see. So ROC curve, and we say injuries. So that's because that's the truth. And then prediction injuries, because that's the predicted probability. And then we get, that's an ROC curve right there. And then you can do auto plot, or you can make one yourself. We'll do this one to be fast. So that's what the ROC curve looks like. So, you know, not bad. Like this is real data, right? This is real and messy data. So, like nothing, you know, we got this ourselves, right? So this is not so bad. And there we go. Okay, so now let's talk about how we're going to save the model. And this is the last thing we're going to do. So this is we train a model. You know, it is acceptable to me, at least, for moving forward with this model, for using it as a demonstration for how to do model ops kinds of tasks. So we need to save it so that we can then use it later and see how does it do over time. So what we need to do for this model is we're going to do a couple things. We are going to do what's called butchering it. So there's a function called butcher, and so we take the that same dot workflow, this thing right here, and we're going to call this this is the model. So crash fit model, like this. So when we have butchered it, what we do is we try to make it as small as possible. So if we predict crash fit, what I want to do is show you that they're the same. Crash fit workflow one, let's see, one like this, and let's just take what from the crash test. Let's take like that, and then let's do the same thing after we've butchered it. So what butchering does is it makes it as small as possible. The bag tree model is already pretty small, so it doesn't really have a ton of let me just do this to clarify what it is that I'm doing. So the idea of butchering is that it streamlines the model to make it smaller. So the lobster object size like this. So if we put the crash fit, crash workflow model, and if we do the same thing but for the original, we'll see that it's a little bit bigger. Oh gosh. Oh, did I not do it? Did I not butcher it? Oh, well, it didn't really make any difference at all. Okay, so sometimes removing stuff out of the recipe can and make it smaller. This one, it didn't really make any difference at all. So that's that. But it's often a good idea to try and notice that you can still predict with it. So the idea of butchering is that it takes out everything that you don't need, and you only end up with what you need for prediction. So you would not end up with like things you need for finding variable importance or anything you need for analysis. All you have with at the end is what you need to make a prediction. So looking, at least trying to butcher can be helpful. It turns out this model is already very streamlined because bag trees are like that. So we didn't really gain anything. So, but that's that. So, and this model is not so big to start with. So that's pretty good. Okay, so now what we can do is we can save this model to keep it later. So I like to do this with there's a couple different ways. You can use save RDS. You can do write RDS, something like this. And so what I'm going to do is I'm going to say crash of the model, and then it's pretty nice sometimes to use the here package the here package for this, and I'm going to put it in a place called data, and I'm going to call it crash workflow model.rds like this. And the other thing that I'm going to save is the metrics, because those are going to be really important for monitoring how the model is doing. So I'm going to keep the metrics for the testing data. I think these were almost exactly the same, so it doesn't. So I think you know what? I'm going to keep the metrics for the training data because it has a mean and a standard error because it was done with 10, and so that spread is going to help me understand if I'm like within where I would expect to be. So I am going to save these. And so, if you want, you can like pipe to write our this, and actually I'm just gonna save it as a CSV because it's so small and the flat files are nice, and I'm gonna call this crash model metrics like this, and I'm gonna save this one as a CSV because it's just it doesn't need to be a binary file. It can just be, it's just a tiny little CSV like that. All right, so then I will just save that. It's gonna notice it takes a second to write that our binary file, and it does have to like read that in when it's gonna like predict. So that's why we want that thing to be as small as possible.
All right, we did it. We downloaded that data from the City of Chicago's Open Data Portal. We did exploratory data analysis. Then we trained our model, evaluated our model so that we know what performance we will expect to see, and then we save the model so that we can use it in the future. We can deploy it, we can monitor it, and so you can look for next steps in this model. And these other kinds of steps and what we might do with a model coming up soon. So look for those soon.